All right, so today we are talking about finding the areas of polar functions. Um, so I'm going to give you a formula for area in a second. To understand why this formula works, let's say I have a circle. This circle has radius 4. You know the area of the circle. And let's say I have an angle of 60 degrees, or what is 60 degrees? Pi over 3. What's the area of this sector of the circle? Well, it's going to be, you could think of it, I still convert everything to degrees in my head. 60 over 360, or that's the fraction of the circle, or pi over 3 over 2 pi, or would times, so it's pi r squared times the percentage of the circle, whatever that percentage is, which is pi times 4 squared over 6, I think. It's possible I made a mistake, but I think that the idea of the formula for the area of this sector is whatever percentage of the circle this angle is, then you're going to multiply the area of the whole circle by that angle. Okay? This is just circles, but this motivates the theory for finding the area around any curve. In fact, we're going to think of very little right triangles. And we're going to think of the area around a circle as 1/2 f of theta squared d theta. Okay, so now this is 1/2 times the base times the height, and then it's going to be an integral from A to B. So if I have a curve that looks like this, let's say this is theta is equal to A, this is theta is equal to B. Your formula when you're using, and this is R is equal to some function of theta. Your formula now for area is going to be area is equal to 1/2 the integral from A to B of f squared theta d theta. And like what I think about that as like a tiny little laser that just shoots arrows and it sweeps around in a circle. It sweeps clockwise. It sweeps counterclockwise in a circle and does a better job sweeping than me because I've left parts out that get unswept. But the machine, the sweeper, the laser machine, doesn't leave anything unswept and it gets every single little piece in here. What you do have to be careful with is to make sure that it's your A is an angle that's less than your B, because we have this unit circle, right? Where if I go around in a circle, we think of this as 0 and we think of this as 2 pi. So like, let's say I wanted to get the area from here to here. And then let's say this is 7 pi over 4. Well, if I did the integral from 7 pi over 4 to 0, that's actually going to sweep the opposite way that I want it to. What I would want to do in this case is change that to negative pi over 4 to 0. So you do have to keep that in mind. And you'll see this come up. And I'll just do an example that may be kind of, I don't know, it could be kind of high level, but I think you can follow along with my reasoning here. Let's see, I'm going to do R is equal to 2 cosine 4 theta. And I'm going to do R is equal to 2. Boom. It's pretty, right? Wait. Can we make it prettier? Let's go reverse contrast. All right. So what I'm trying to find, let's say I'm trying to find all the area that's outside this little rose petal. This is a petal with 8 leaves because the 4 is inside of here. And that's outside of, outside of the flower, but inside of the circle. So basically what I need to do is find the area of the circle and subtract the area that is of the flower. The area of the circle is going to be easy. That's pi r squared. That's 4 pi. The area of the petal, well, let's see. First thing I always want to do with these is look at, and Desmos makes this really easy to do. It's just I play around with these domain here to see how long it takes to make one full complete cycle. Okay, so 0 to 2 pi. And then the next thing that I'm thinking is it would be easier to just find the area of one petal and multiply that by 8. That's a little bit less complicated. So let's say if I do to pi over 4. See, pi over 8. Oop. Pi over 8 looks good. So 0 to pi over 8 is only half of it. So if I go the integral from negative pi over 8 to 8, I'm going to get exactly one petal. So I could do 1/2 times the integral from negative pi over 8 to pi over 8 of 2 cosine 4 theta squared d theta. And I get that number. That probably is something related to pi. You may even be able to do this on paper. I'm above that, but you are not. So this is 8 times that because there's 8 of these flowers, remember? So now if I'm looking at this, I would have 0 to 2 pi. I've got the area that's inside the circle. I would just take 4 pi minus 2 pi, and I get 2 pi. Okay. There's another one that's on today's classwork that's like that. It's a little bit easier with that example. You should be in good shape. There's another one that's like, I'm not going to show you exactly how to do it, but let's say r is equal to 2 plus 2 cosine theta. And let's see, r is equal to 3 cosine theta. Let's change that. Let's make that 5 cosine theta. All right, that looks right. So now let's say you want some kind of area here. There's a lot of different areas that you could be looking for. For example, you might look for this area. Let's see. You might look for this area right here. In that one, you want to have to keep in mind which is on the outside. So let's say this is A and this is B. That would be 1/2 integral from A to B of, let's call this R2 and this R1. This would be R2 squared minus R1 squared d theta. However, that might not work because you have to check what your boundaries are. And in this case, 2 plus 2 cosine theta makes one complete circle in 2 pi radians, whereas 5 cosine theta only needs, like if I go pi over 2, it gets halfway around the circle. That's just how the cosine works. So these things are not going to be, it's not going to be as easy as you think. But what you have to do is figure out what these points are. You're going to have to figure out specifically what this point is. And then you can figure out say you want this area now. You might think that if I do the integral from b to whatever this is, I think that might be pi over 2, that I'm going to get the area that I want. However, when you do that, you're going to get this area right here. So what you need to do is figure out how to get that area and subtract off the area that you don't want, which is this area right there. And I think that's probably confusing as your first introduction to polar area functions. But as you go through today's classwork, it'll make more sense, and hopefully it'll make the classwork a little bit easier for you.